We present a system that applies a custom-built pan-tilt zoom camera for laser pointer tracking in arbitrary real environments. Our prototype consists of 2 video cameras, a low-resolution wide-angle context camera, and a high-resolution pan-tilt zoom detail camera. A microcontroller and 2 stepper motors with their controllers are applied for rotating the detail camera and an attached laser module. Both cameras are directly connected to a PC that analyzes their video images and controls motors, camera settings, and the laser module over the microcontroller. When the PTZ camera is positioned at the architectural site, a full automatic self-registration is carried out. For registration, the PTZ camera samples the depth of the environment using the attached laser module. To avoid unnecessary motor movements and resulting long registration times, the sampling is not carried out uniformly along the hemispherical sampling space of the PTZ camera. Instead, an adaptive multi-resolution sampling is carried out. This results in a low-resolution sampling for largely planar environmental sections and in a high-resolution sampling for geometrically more complicated sections. The resulting point cloud can be triangulated, intermediate depth values can be interpolated, and normal vectors can be computed. Since the sampled points are measured in device coordinates, the rigid transformation matrix can be estimated numerically by finding the best geometric match between the point cloud and the measured reference model stored in the database. Besides sampling geometry, other surface parameters can be captured during this process. The diffuse surface reflectance, for instance, is captured for each discrete perspective of the detail camera under a short and a normal exposure. The individual image patches are later blended using linear ramps to create seamless overlap and stored in 2 spherical environmental maps. After the camera is registered to the surrounding scene geometry, unstructuredly aligned projectors can be registered automatically with respect to the common world coordinate system. Therefore, all projectors are calibrated sequentially. This is achieved by projecting coded patterns, detecting these patterns with the PTZ camera, and establishing a correlation between image coordinates on the projected patterns on each projector's image plane and their 3D coordinates in the world coordinate system at which they are projected. Finally, the intrinsic and extrinsic parameters of each projector can be estimated numerically. After calibration, the PTZ camera can be used to track a single visible laser spot that appears on a scene surface and is within the viewing range of either the detail camera or the context camera. Receiving continuous information about the laser spot's 3D world coordinates on the surrounding surfaces and its current state, on-off, allows the interaction with a projector-augmented environment. Basic object manipulation techniques like rotation, translation, and scaling are supported. Simple spatial and time-encoded gestures are currently used to trigger events such as changing the interaction mode. Another example applies a laser pointer to interact with an architectural on-site planning tool for color simulation. Thereby, a picking event is triggered by holding the laser spot still within a particular region for 2 seconds. If visible in the detail camera, the position of the laser spot can be estimated. If the spot is lost, the context camera delivers information for realigning the detail camera. There are 2 reasons when this can happen. Either the laser pointer is turned off and turned on again, pointing somewhere outside the current perspective of the detail camera, or the movement of the laser spot is too fast for stepper motors and detail camera to track. While a projector-based augmentation is best suited for the visualization information directly on the surfaces, such as lighting, color, and material simulations or geometric structures with small depth variations, video see-through augmentation supports visualization of free-floating 3D structures from the controllable perspective of the PTZ camera. Due to the environment's known geometry, correct occlusion of virtual structures can be achieved. Yet, the PTZ camera itself can be used for a rough pose estimation of active LED markers. Once detected, the full 6 DOF pose of the marker and world coordinate system is delivered. This technique can be used for making rough indications of the observer's position or other positions and orientations within the world coordinate system. Knowing the observer's position can be used to render view-dependent 3D structures that are virtually located behind the physical surface. This simple tracking technique proved to be a useful tool for many view-dependent architectural visualizations without notably increasing the system complexity through an additional tracking device.